So here we're asked to find the limit as h approaches 0 of f of x plus h minus f of x over h, as well as the limit as x approaches a of f of x minus f of a over x minus a for a bunch of different functions. This is our first homework assignment of the derivatives unit, and these are the two limit definitions of the derivative that we've talked about. So we're just going to do each of the problems here, and I'll kind of talk my way through them. So to find the limit as h approaches 0 of the difference quotient, right, that being our f of x plus h minus f of x over h, we'll start off by writing the limit as h approaches 0. Don't forget to write the limit every time. And then we'll evaluate f of x plus h. Well, that just means replace all the x's with x plus h's. So x becomes x plus h. Then we'll subtract f of x, which is just x, and divide by h. We should see that the x and the minus x in the numerator cancels out, leaving us with a limit as h approaches 0 of h over h, which we note is an indeterminate form, but we know that h divided by h is equal to 1 for any values when h is not 0, and since h is approaching 0, it's not 0. And we also know that the limit of a constant is the constant. So we end up with 1. That limit is equal to 1, means that the derivative of x is 1. And if we choose to do this for the other limit, we'll have a limit as x approaches a of f of x, which is just x, minus f of a, which is just a, divided by x minus a. And if you plug in a to both of those, you see that it's indeterminate, but we can cancel out the x minus a over x minus a. We end up with the limit as x approaches a of a constant, which just gives us 1. So once again, we get 1 either way. We'll note that as we go through here, for some of the, for these very basic functions, we're going to just get a number. But for most of them, we won't end up just getting a number. And the one on the left, the f of x plus a, h limit's going to give us something in terms of x, and the other one's going to give us something in terms of a at the end. So let's take a look at this one. We'll do a limit as h approaches 0 of f of x plus h, which just means, again, replace the x with x plus h, so 2 times x plus h, minus 3. And then we'll subtract from that f of x, which is 2x minus 3, all over h. We will simplify out that numerator as much as we can, and distribute the 2, so 2x plus 2h, minus 3, and then minus 2x, and then plus 3, divided by h. And we should see that everything that is in that numerator that doesn't have an h in it is going to end up canceling out. The 2x and the minus 2x will cancel, and the minus 3 and the plus 3 will cancel. So we're just left with a limit as h approaches 0 of 2h over h, which is indeterminate if you plug in 0, so we'll cancel the h's to get a limit as h approaches 0 of 2, which we know to just be 2. For the other limit, we'll do the limit as x approaches a of f of x, which will just be 2x minus 3, minus f of a, and we'll make sure to put that into parentheses. F of a will be 2a minus 3, and we'll divide that by x minus a. When we distribute the minus sign in the numerator, we end up with 2x minus 3 minus 2a plus 3. And it's still all over x minus a. And we should see that the minus 3 and the plus 3 will cancel out, leaving us with a limit as x approaches a of 2x minus 2a over x minus a. We then will factor out the 2 from the numerator so that it'll cancel with the, so the x minus a in the numerator will cancel with the x minus a in the denominator. We just have a limit as x approaches a of 2, which of course is just 2. So those are the easy linear ones. They start to get a little bit more complicated once the functions are no longer linear. So let's take a look at this parabolic function, see if we can find the derivative or find these two different limits. So for the first one, we'll do a limit as h approaches 0 of f of x plus h, which means replace the x with x plus h, so x plus h squared. And don't forget the plus 1 that's part of f of x plus h. A lot of people tend to forget the constants at the end sometimes, so be careful about that. And then we'll subtract our function, all divided by h. We should be able to distribute out x plus h squared. All right, that's just a perfect square trinomial when we distribute that out. That should be x squared plus 2xh plus h squared, and then plus 1, and then minus x squared, and then minus 1. And we'll see that the same thing that happened with the last problems was that everything that didn't have the h in it canceled out, like the x squared with the minus x squared and the plus 1 with the minus 1, leaving us with just a limit as h approaches 0 of 2xh plus h squared over h. And you can choose to either factor an h out of the numerator to cancel it with the h in the denominator, or you can just divide term by term by h. I'm gonna just divide term by h. I'm gonna do the 2xh and divide it by h, and the h squared and divide it by h. And that's going to give me a limit as h approaches 0 of 2x plus h. And as h goes towards 0, 2x is just 2x because there's no h in it, and h is 0. So we just get a final answer of 2x. To do the other limit, we'll start with the limit as x approaches a of f of x, so x squared plus 1, minus f of a, which will just be a squared plus 1, all over x minus a. And we'll see by the time we get to the end of this one, we're going to get the same expression that we got with the blue one with f of x plus h, except it's going to be in terms of a instead of in terms of x. So we'll see the plus, oops, I gotta make sure I put that in parentheses there. So when we distribute that, we see that the plus 1 and the minus 1 cancel out. So we really just end up with x squared minus a squared in the numerator, which is a difference of squares. So we will factor it into x plus a times x minus a over x minus a, allowing us to cancel the x minus a in the numerator and the denominator, leaving us with a limit as x approaches a of just x plus a. And as x goes to a, well, then x becomes a, and a stays as a. So a plus a is equal to 2a. And so the real difference here is that when we talk about the limit as h approaches 0 of the difference quotient, f of x plus h minus f of x over h, we're getting a generic expression that's in terms of x. And for the other one, we're just getting the generic expression for a specific constant a. And so most times you would see this as like a limit as x approaches 3 of f of x minus f of 3 over x minus 3. And you'd know you'd be finding the derivative at 3. All right, they're starting to get a little bit more complicated. We got both a second degree and a first degree x term in there. We may start running out of room on a single page and have to go to a new page, but that's okay. We'll start with a limit as h approaches 0 of x plus h squared plus x plus h plus 3. We've replaced both x's with x plus h. And then we'll subtract x squared plus x plus 3 from that and divide it all by h. Now we'll do the same distributing of the x plus h squared and the minus sign to our function as we did previously. X squared plus 2xh plus h squared plus x plus h plus 3 minus x squared minus x minus 3. And of course, it's still all over h. So now we should see the exact same thing as what we saw before, which was all those terms cancel out. They don't have the h in them, so the x squared and the minus x squared, the plus x and the minus x, and the plus 3 and the minus 3. We should be able to get rid of all of those terms. leaving us with just a limit as h approaches 0 of 2xh plus h squared plus h, all divided by h. And of course, they all have an h term in them, so we can term by term divide, giving us 2x, because 2xh divided by h is just 2x, plus h. Don't forget my limit as h approaches 0 in the front here. So h squared divided by h is just h, and then h divided by h here is 1. And be careful, I see a lot of students that say, oh, h over h, that cancels out, and they forget to put the plus 1 at the end. So make sure you put the plus 1. And now as h goes to 0, 2x is 2x, h is 0, so that goes away, and we end up with 2x plus 1. Okay, so we'll do that one again, except this time we'll do it as a limit as x approaches a. And I'm going to just put up in the corner here a little reminder, f of x was equal to x squared plus x plus 3. And so we can immediately go in and fill in our f of x. So there's x squared plus x plus 3, and we will subtract a squared plus a plus 3 all over x minus a. And these ones end up getting a little bit trickier. So we'll see if I go in here and cancel out the plus 3 with the minus 3. I'm just going to kind of skip that little step, right? I have a plus 3 there, and then a minus 3 that gets distributed. So I'm going to cancel those out. We'll have x squared plus x minus a squared minus a over x minus a. And we'll see that these ones do get just a bit trickier. We have to kind of use a little technique that we've used a bunch of times in our limits unit, which is to separate this into 2 different limits. So you kind of want to look for things that might factor and things that might cancel out nicely. So I'm going to factor, or not factor, but separate this into these 2 limits. And since it's all addition or subtraction in the numerator, I can separate them however I wish, as long as I keep the same denominator for them. So the way I've done it is giving me an x squared minus a squared, which I know is a difference of squares and will factor. And then on the other side, I've just got x minus a over x minus a, which I know should simplify down to 1. So if I factor x squared minus a squared, I get x minus a, x plus a over x minus a. And then the other limit just becomes a limit as x approaches a of 1, because x minus a over x minus a just gives you 1. That should allow us to say this becomes a limit as x approaches a of just x plus a for the first limit, and then plus, we'll put that in parentheses, not that it really matters, but to be mathematically correct, we should separate them stuff. Limit as x approaches a of x plus a plus 1, and then as x goes to a, that becomes, I was going to write my 2a already, it becomes a plus 1, or just 2a plus 1. All right, for our next one, 3x cubed minus x minus 1. So this one's going to be a little more difficult here on our f of x plus h to start with, because now we've got 3 times x plus h cubed, which means we need to know how to distribute out the sum of cubes using Pascal's triangle. And then we'll subtract x plus h. Be careful to put that x plus h in parentheses. Make sure that minus sign gets applied to both things. And then minus 1. And then we'll subtract f of x, so minus 3x cubed minus x minus 1, all over h. And as h goes to 0, our limit as h goes to 0, just real quick, we'll put up a new page just in case we don't remember Pascal's triangle, right? 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. This row gives us the coefficients for expanding out x plus h to the 3rd power. So it should be 1x to the third with an h to the 0, but we don't write that because h to the 0 is 1. And then plus 3x squared h to the first plus 3xh squared, and then plus h cubed. Right, so we use those coefficients of 1, 3, 3, and 1. And the powers of x start at cubed and descend down to x squared, x to the first, and then x to the 0, which is just 1, so we don't write it. Whereas the h powers start at h to the 0 and go up h to the first, h to the second, h to the third. So we've now got 3 times x cubed plus 3x squared h plus 3x h squared plus h cubed minus x minus h minus 1 minus 3x cubed plus x plus 1 all over h. And we're going to just cancel some stuff out here. We can see that the plus x and the plus 1 will cancel with a minus x and a minus 1. And when I distribute this 3 to the x cubed, that's going to become 3x cubed with a minus 3x cubed will cancel. And we'll just make sure we remember to distribute that 3 to everything else there. So we now have a limit as h approaches 0 of 9x squared h plus 9x h squared plus 3h cubed. And then we have a minus h term in there that we don't want to lose and forget. And it's still all over h. And when we do a term-by-term division here, we'll end up with 9x squared plus 9xh plus 3h squared minus 1. Well, 9x squared is 9x squared when h is 0. 9xh when h is 0 is 0, as is 3h squared, and minus 1 is just minus 1. So we end up with 9x squared minus 1. So we will now we'll now do this one as a limit as x approaches a. And I'll put my function up here again, just so I've got it. F of x was, I believe, 3x cubed minus x minus 1. So we'll have a limit as x approaches a of f of x minus f of a all over x minus a. And we're going to use a similar process as to what we saw with the last one. We should, I think, see that the minus 1 here and the minus 1, or we have a minus 1, is going to be a plus 1. So those will cancel out. So really, we're just left with a limit as x approaches a of 3x cubed minus x minus 3a cubed plus a. And when we do that, we should see that if we group the 3x cubed with the minus 3a cubed, don't forget this x minus a, with the x minus a in its denominator, and then factor out a negative 1 from the negative x plus a, which will make this a subtraction between the limits. Well, if I factor out negative 1 from negative x, that's positive x. And if I factor negative 1 from positive a, that's minus a. And I've now got terms that cancel again. So we should see then that the first one here, we can factor the 3 out of it, right? And it's 3 times x cubed minus a cubed. We'll go back over here to our little bit of side work we were doing. X cubed minus a cubed is a difference of cubes. We should know that that factors to x minus a, x squared plus ax, or xa, well, we'll write ax, plus a squared. Fix that, plus a squared. And that's how a difference of cubes factors. So we'll make sure that we turn that into exactly that, x minus a, x squared plus ax plus a squared, all over x minus a, and then minus a limit as x approaches a of 1. I'm kind of running low on room here, so we'll come up here. We can cancel the x minus a and the x minus a. And so now we're just left with a limit as x approaches a of 3 times x squared plus ax plus a squared. And then we have this minus 1 afterwards. So we'll subtract the 1 part because the limit as x approaches a of 1 is just 1. And now we can evaluate. This becomes 3 times a squared plus, well, a times x is approaching a is a times a, so that's a squared. And a squared is still a squared. And then minus 1. And now we have 3a squared inside our parentheses, giving us 9a squared minus 1 in the index. All right, we're going to move away from polynomial functions. So we're going to now look at just the most basic rational function that there is. We're going to look at the reciprocal function. We'll start off with the limit as h approaches 0 of 1 over x plus h minus 1 over x, all over h, of course. And we see that this is a complex fraction. So when we're dealing with complex fractions, we always want to get a common denominator, at least within the portion of the fraction that has extra fractions. So right here, I've got x plus h, so that's going to be part of my common denominator. And here I've got x, so that's going to be the other part of my common denominator. It's going to be x times x plus h. And we're not going to want to distribute that out because we're going to want to try and get it to, well, we could distribute it out, but I think it's often easier if we don't, because sometimes it'll cancel out. We won't in this one, but sometimes it does. So to turn 1 over x plus h into something that has a denominator of x times x plus h, we got to multiply it by x over x. And then to turn 1 over x into something that has a common denominator, we're going to multiply it by x plus h over x plus h. And don't let me forget here, my limit as h approaches 0. And this is all, of course, over h. And so now we can combine our terms in the numerator into one fraction. So we'll have x minus x plus h all over x times x plus h. And in the same step here, let's think about what happens if I have h over 1 in my denominator. Well, it's currently a fraction divided by another fraction, right? I have one fraction here divided by another fraction here. Well, how do we deal with that? Well, we have a fraction divided by a fraction. We take the reciprocal of the denominator and we multiply. So this, I'm going to say, let's just multiply by 1 over h, which means that that h in the denominator just gets thrown in with my other new denominator. Then we can go and say this is a limit as h approaches 0 of x minus h over x times x plus h times h. The x minus x will cancel, and we just have negative h over x times x plus h times h. The h in the numerator and the h in the denominator cancel. And we're just, x approaches, it's h approaches. Limit as h approaches 0 of negative 1 over x times x plus h. Well, that's negative 1 over x times x plus 0. X plus 0 is just x, and x times x is x squared. So now we'll do this one using the limit as x approaches a. So I'll put my function up here in the corner again. We got f of x is 1 over x. So we will do a limit as x approaches a of f of x minus f of a all over x minus a. We'll want to get a common denominator again. This time that common denominator is just going to be a times x. So this will be a limit as x approaches a of a over ax minus x over ax all over x minus a. And we can then see that becomes a limit as x approaches a. If we combine the numerator together, it's a minus x over ax. And just like we did before, this x minus a can be written as x minus a over 1. And multiplying by the reciprocal just puts that into the denominator. And perhaps at first glance, it doesn't look like anything's going to cancel out nicely here. But we'll note that a minus x and x minus a could cancel if I just factored a negative 1 out of one or the other. So let's do that from the numerator. I'll have a limit as x approaches a of negative x minus a over a x times x minus a. And so now all we have to do is see what happens as x goes to a. Well, the x minus a's will cancel. So we have a limit as x approaches a of negative 1 over ax. And as x becomes a, that becomes negative 1 over a times a, or negative 1 over a squared. All right, for f of x equals 2 over x squared, we'll again start with our difference quotient one. The limit is h approaches 0 of f of x plus h, which in this case will be 2 over x plus h squared, minus f of x, 2 over x squared, all over h. We'll do the same thing we did before. I'm going to kind of write it in one step here. This time I'm going to say we're going to multiply by x squared over x squared. And we're going to multiply by x plus h squared over x plus h squared, because that's going to give us a common denominator in our numerator. So this becomes a limit as h approaches 0 of 2x squared minus 2 times x plus h squared all over x squared times x plus h squared. And we'll do the same trick as before, h over 1 in the denominator, take its reciprocal, multiplying that h goes straight into your other denominator. So now we will simplify out that numerator that we've got. It's kind of a mess. Limit as h approaches 0 of 2x squared. And then we know that x plus h squared, we know that this is x squared plus 2xh plus h squared. So if we're going to distribute a minus 2 to that, we'll get minus 2x squared, and then minus 4xh, and then minus 2h squared, all over x squared times x plus h squared times h. And then we're going to kind of simplify this down a little bit. The 2x squareds will cancel. And we'll write it as a limit as h approaches 0 of negative 4xh minus 2h squared all over x squared times x plus h squared times h. And we can see that both terms in the numerator, just like every other time, all the terms in the numerator still have an h in them. So they'll cancel with the h that we have in the denominator. So this now becomes a limit as h approaches 0 of negative 4x, because the h cancels out, minus 2h, because the h squared becomes an h. And then it's an x squared and an x plus h squared down here in the denominator, because we've canceled out that h that was down there. It would seem we're now ready to plug it in. Okay, we can plug in 0 for h. So we now have negative 4x in the numerator because minus 2h will become 0. And this h will become 0, so it's just x squared times x squared in the denominator, which we should know to be x to the 4th. And then we can simplify that down just a bit, cancel an x from the numerator with an x from the denominator, and we get negative 4 over x cubed. And now we'll do it the other way. We've got f of x equals 2 over x squared as our function, and we'll do a limit as x approaches a of f of x minus f of a all over x minus a. We'll do the same thing to get a common denominator that we've done before. So limit as x approaches a, we'll multiply the first fraction, the 2 over x squared, we'll multiply by a squared over a squared to give us 2a squared over a squared x squared. And then we'll subtract that second one, we'll multiply by x squared over x squared, so minus 2x squared over a squared x squared, and I'll still write it as over x minus a here for now. We'll throw that x minus a into the denominator of our numerator in a second. So now we have a limit as x approaches a of 2a squared minus 2x squared over a squared x squared times x minus a. And if we factor a 2 out of the numerator, we're going to see a squared minus x squared. Now I'm going to write this off to the side here. If I factor out that 2, I have 2 times a squared minus x squared, which we know is a difference of squares, which would become a minus x and a, not x, well, I guess it's fine if I write x plus a minus x, a plus x plus a is the same. But we note that these two don't quite match up. So if we had x squared minus a squared, though, in the numerator, let's think about that for a second. If we had x squared minus a squared, now we don't have this, but if we have this, and we could have this, if we, instead of factoring out a 2, factor out a negative 2, then when we factored the x squared minus a squared, we have x minus a, x plus a, and then we'd have this nice matchup here to cancel out. So let's factor a negative 2 out of that numerator. Leaving us with, as we just showed, x minus a, x plus a, because it's x squared minus a squared if we do that, all over a squared x squared times x minus a. And then we can cancel out the x minus a's. So we'll have a limit as x approaches a of negative 2 times x plus a over a squared x squared. And as x goes to a, we end up with negative 2 times a plus a over a squared times a squared. Well, a plus a right here is just 2a. So negative 2 times 2a would be negative 4a. A squared times a squared will be a to the 4th, and it becomes negative 4 over a cubed. Alrighty, for our next one here, for number 8, we've got another little rational function, 2 over x plus 3. So we'll start out with a limit as h approaches 0 of 2 over x plus h plus 3, because that's what we get if we plug in x plus h for x, minus 2 over x plus 3, just our function, all over h. We'll want the common denominator to be x plus h plus 3 times x plus 3, which means I'm going to have to multiply the first fraction here by x plus 3 over x plus 3. Right, that one needs x plus 3. And multiply this one by x plus h plus 3 over x plus h plus 3. And so we end up with a limit as h approaches 0 of 2 times x plus 3 minus 2 times x plus h plus 3 all over that new common denominator, which we were trying to get, which was x plus h plus 3. There we go. Times x plus 3. And it was all over h, which, as we've seen a bunch of times, just kind of falls into our other denominator there. Well, let's just simplify out in our numerator here and see what we get. We've got a limit as h approaches 0 of 2x plus 6 minus 2x minus 2h minus 6 all over all that same stuff, x plus h plus 3, x plus 3, and h. And we see that the 2x and the minus 2x here should cancel, and plus 6 and the minus 6 should cancel. So we end up with a limit as h approaches 0 of negative 2h over x plus h plus 3 times x plus 3 times h. The h's, of course, will cancel. It becomes a limit as h approaches 0 of negative 2 over x plus h plus 3 times x plus 3. As h goes to 0, that's negative 2 over x plus 3 times x plus 3, because this h goes to 0. X plus 3 times x plus 3 is just x plus 3 squared. All right. Making our way to the end here. We've got f of x is 2 over x plus 3. And so if we're looking at that, and we're going to do a limit as x approaches a of f of x minus f of a all over x minus a. We'll need to do the same strategy we've been doing, which is to get a common denominator, which is going to be a limit as x approaches a of 2 times a plus 3 minus 2 times x plus 3 all over x plus 3 times a plus 3, because we've multiplied the first fraction by a plus 3 over a plus 3, and we've multiplied the second fraction by x plus 3 over x plus 3. And then we still have this x minus a that was in the original denominator, which gets thrown in with our new denominator. So now we should be able to simplify out that numerator a bit. So we'll have a limit as x approaches a of 2a plus 6 minus 2x plus, not plus 6, minus 6, because we're going to distribute that minus sign through, all over x plus 3, a plus 3, and x minus a. We can see that the 6's, 6 and the negative 6 will cancel. And if I have 2a minus 2x and factor a 2 out of it, I have 2a minus 2x, that's 2 times a minus x. But a minus x doesn't cancel with anything, but x minus a would. So kind of like we did before, we're going to factor the negative 2 out of it to turn that numerator into an x minus a instead of an a minus x. So this is a limit as x approaches a of negative 2 times x minus a over x plus 3, a plus 3, and x minus a. When the x minus a is cancel, we have negative 2 over x plus 3, a plus 3. It's a pretty terrible a, but it's an a. And as x goes to a, we have negative 2 over that x is the only x we have. It becomes an a. So it's a plus 3 times a plus 3 in the denominator, or a plus 3 squared. Yeah, just 2 more to go here. We're going to do our first radical function here, so square root of x. So for this one, we're going to have to use another sort of new technique that we haven't seen since the limits unit. F of x plus h is root x plus h, and then minus root x all over h. And one of the things we talked about in the limits unit was one way to solve an indeterminate limit, like all of these are, particularly when you have radicals involved, is to just multiply by the conjugate. So we're going to do that. The conjugate of root x plus h minus x is root x plus h plus root x. And so we'll do the same thing to our denominator. What we're not going to do is distribute out the denominator. You see that's a pattern all along the way, as we don't normally want to distribute those out. And so now we'll go in here and we'll see what happens nicely to our numerator, right? Root x plus h times root x plus h is x plus h. And minus root x times plus root x is minus x. But the other terms, and this is the nice thing about the conjugate, right? This is a difference of squares. So when I do, I'll mark these in a different color. When I do root x plus h times root x, I get root x times root x plus h. And when I do negative root x times root x plus h, that's a negative of what I just had a positive of. Those two terms cancel each other out, right? The outside terms and the inside terms cancel. And we're just left with this. So very convenient. So we now have h times, it's a little bit too long of a radical, but h times root x plus h plus root x. The x and the minus x in our numerator will cancel, giving us a limit as h approaches 0 of just h over h times root x plus h plus root x. Make sure that stays in parentheses. I see a lot of people forget the parentheses in the denominator. And then they try and distribute things out incorrectly, or they can't get their h's to cancel. So now this just becomes a limit as h approaches 0 of 1 over root x plus h plus root x when we cancel the h over the h. And from there, we just plug in 0 for h. We have 1 over root x plus root x, which is 1 over 2 root x. All right, let's do this as a limit as x approaches a. So f of x is root x. As we do this as a limit as x approaches a, we'll have root x for f of x and root a for f of a over x minus a. And we're going to just need to use the exact same technique here to deal with the radicals. We'll just multiply by root x plus a over root x plus a. We could, of course, also factor x minus a as a difference of squares. We learned that technique in the limits unit, right? That sometimes these just, anything that's x minus a is a difference of squares if you just take the right square roots. But we'll just multiply by root x plus root a, since that's what I said we would do from the beginning here. Please use the conjugate. If you do it the other way, there's no problem with that. So we have a limit as x approaches a of root x times root x is x, and root a times negative root a is minus a, and the middle two terms cancel out again. Root x times root a and negative a, root a times root x, those cancel out. And so now in our denominator, we have x minus a and root x plus root a. The x minus a's cancel. And we have 1 over root x plus root a. And as x approaches a, that's 1 over root a plus root a, or 1 over 2 root a. All right, we've almost made it here. We're on to the last problem. So we'll do our limit as h approaches 0 for 1 over root x. 1 over root x, if we plug in x plus h, is just 1 over root x plus h. And then minus 1 over root x all over h. So this one's a fun looking one. We can see already that it's a complex fraction, which means we're going to have to do a common denominator. But it's also got the radicals in it, so we're probably going to have to do some stuff with the conjugate as well. So we'll start off by getting the common denominator. And I'm just going to kind of do this here, root x and root x. And this one needs a root x plus h and a root x plus h. So if I do that, we end up with a limit as h approaches 0 of root x minus root x plus h all over this h and root x plus h. And now to deal with that, we have root x minus root x plus h. So I think we're probably used to what we need to do with that is we need to just multiply it by the conjugate. We'll switch here to new color here, and we'll just do it right here, root x plus h. And make sure that goes in parentheses so we know that it's being multiplied by the whole thing. We'll do the same thing here, root x plus h. And once again, we will not distribute out that denominator, but we will with the numerator, because the numerator is just going to give us a limit as h approaches 0 of, well, root x times root x is x. And the last terms become minus. And then make sure you get that x plus h in its parentheses. Don't just write minus x plus h without parentheses, because then you're going to be, in the end, you're going to be off by a negative if you don't do that. And down here, we'll just leave it as is, h root x plus h, and root x plus h. I think we can see that the x and the minus x will cancel. So we're just left with a limit as h approaches 0 of negative h over all that fun stuff again, h root x plus h, and root x plus h. The h's will cancel. We're running out of room down here, but we can make it work. Negative 1 all over, if the h's cancel, then the root x is still there, the root x plus h is still there, and the root x plus h is still there. Now as h goes to 0, we've got negative 1 in the numerator, we've got root x, we've got another root x because the plus h is 0, and then we've got root x plus root x. Okay. Well, root x times root x is just x. So that's negative 1 over x. And root x plus root x is 2 root x. And so we would normally write this as either negative 1 over 2x root x, right, as a final answer. Or if you want, and let's just draw an arrow over here, we could also call that negative 1 over 2x to the negative 3 halves, or negative 1 over 2x to the positive 3 halves if we keep that x to the positive 3 halves, the denominator. All right, and we're basically there. We've got function up here again, f of x equals 1 over root x. And now we'll just do it as a limit as x approaches a. And we'll be finished. So it's a limit as x approaches a of 1 over root x minus 1 over root a all over x minus a. It's a complex fraction, which means get a common denominator and the piece of it that requires it. So that'll be multiplying by root a and root a here. And here, root x and root x. So we now have a limit as x approaches a of root a minus root x all over that x minus a, and then a root x and a root a. We'll need to multiply by our conjugate, or actually this time let's, it's pretty similar to what we did before. Let's factor this out. I don't think this is what I probably did on the answer key that's posted online. I think I probably multiplied by the conjugate, but that's exactly what we did with the previous problem. So let's see what happens if I factor that denominator. We're going to have a limit as x approaches a of root a minus root x. And x minus a, well, x minus a is root x squared minus root a squared. That's just a difference of squares, right? It's root x minus a times root x minus root a times root x plus root a. So let's just do that. And as I look over here, I realize I wrote a for both of those, but obviously it's not an a for both of those. The first one was an a, the second one was an x. So this now factors to root x minus root a and root x plus root a. And we still have down there in that denominator root x and root a. Now we don't, at first glance, again, have anything that cancels, but if we factor a -1 out of the numerator, we should see that we now have root x minus root a in the numerator, which will cancel with the root x minus root a in the denominator. Running out of room on the side there. The root x minus root a's will cancel. So we have -1 over root x plus root a, root x, and root a. And as x goes towards a, this becomes -1 over root a plus root a times root a times root a, which, just like we had before, is -1 over 2 root a times a. So we'll just call it -1 over 2 a root a. And that is how to do all the problems. That's your walkthrough for all the problems on the first homework assignment of the derivatives unit. Remember that all of these limits are just finding us the derivative of the function.